Hi, I'm Zor. Welcome to Unizor Education. Well, today we will continue talking about yet another aspect of the Noether Theorem. She published this theorem in 1918 in Germany. She was a German mathematician, and the thing is that basically it provided a great foundation for theoretical physics. I mean, people like Einstein and other actually praised her as one of the most important mathematicians who basically put the foundation of physics on a very solid theoretical background. Before her theory, we were talking about laws of conservation of energy, momentum, etc., as something which we basically come up empirically based on observations. However, she was able in the theorem to prove that there are some fundamental properties of space and time. If we accept these fundamental properties as axioms, like symmetry or uniformity, so to speak, then the laws of conservation will follow. And today we will talk about one particular case, the conservation of momentum. Okay. Now this lecture is part of the course called Physics Plus, that's for all, and it's presented on unizor.com. I do suggest you to watch this lecture on unizor.com. So you go to unizor.com, go to Physics Plus course, and this is a part which is called Lagrangian. And in particular, this is the Noether Theorem about momentum conservation. Now, there are many different reasons why I suggest you to go to the website. First of all, it contains all the prerequisites, and there are a lot of prerequisites for this lecture, obviously, and it's all hierarchically and consecutively presented in all the courses which are presented on that website, including Math for Teens, Physics for Teens, Math Plus, and Physics Plus. Secondly, the site is totally free. You don't have to sign in, you don't have to subscribe, there are no advertisements, so it's basically pure knowledge for your consumption. And the third, which is also very, very important, every lecture has basically on that website where the video is presented, it has a textual part. And textual part is basically like a textbook for the same subject which is discussed in the lecture. So chapter by chapter they go in sync, the textbook piece and the lecture on the same material, and it's on the same page, so you can watch the lecture and you can read the textbook basically in parallel or sequentially. Alright, so let's talk about this. Now, I would like to point that there are certain things which I will use and I will consider it as basically given, so you really have to know them before approaching this particular lecture. And these things are, first you have to know what is the configuration space of a mechanical system. It's generalized coordinates and generalized velocities. This is all defined previously in previous lectures. Then we need to know a concept of Lagrangian as a difference between kinetic and potential energy. You have to know the concept of action, which is integral of Lagrangian, and you have to know the Euler-Lagrange equation, which I will put here in writing. So if L is Lagrangian, which is T minus U, kinetic minus potential energy, whenever a system is moving along certain trajectory, its generalized coordinates and velocities satisfy an Euler-Lagrange equation, which is partial derivative by any generalized coordinate equal to full time derivative of this. This is derivative by time. So qk is kth component of generalized coordinates, and qk prime is time derivative, which is velocity, kth component of velocity vector, if you can say so. And this is the full time derivative of this. Now, obviously, all coordinates are a function of time, q1 of t, etc., qn of t, where n is the number of degrees of freedom. Again, all information which I'm saying right now is supposed to be known. If it's not, well, you have to go back to previous lectures. So, that's the Euler-Lagrange equation. Now, this lecture is about the conservation of momentum. So what is momentum? Well, if you have Cartesian coordinates in a three-dimensional world, x, y, and z, all of them are functions of time, and during this function of time, obviously we can calculate the vector of velocity, which is basically time derivative of coordinates. These are all functions of time, obviously. So we can have time derivatives. So this is the vector. And now the linear momentum of this particular particle, again, it's a vector with three coordinates, and it's mv, mass times vector of velocity. So in coordinates it would be mx prime, my prime, mz prime. That's in coordinates. So this is vector which is called momentum, linear momentum of movement. Okay, now how else can we actually derive this particular thing if we don't want to use explicit coordinates and explicit time derivatives? Very simply, what is kinetic energy of this particular particle of mass m moving with velocity v? Well, it's 1/2 of mass and vector square. This is basically a scalar product of vector by itself, which is mx square plus y prime square plus z prime square. So these are components of velocity. So if you add by coordinates the squares of velocity components, you will get basically square of its lengths, because it's x prime, y prime, z prime, scalar multiplied by x prime, y prime, z prime, and whenever you will multiply, you will get x prime square plus y prime square plus z prime square. Okay, so from this we can very easily obtain this. Px is equal to dt by dx prime. Partial derivative by x prime, partial, not time derivative, partial derivative of this expression for the kinetic energy by x prime is what? 1/2 m times partial derivative of x prime square, which is 2x prime. 2 and 2 will cancel, and we will have mx prime. Same thing, py prime is equal to partial derivative of kinetic energy by y prime, which is my prime, and partial derivative of kinetic energy by z prime gives you z component of the momentum vector. Great. Now, how about potential energy? Now, we've talked about kinetic, how about potential? Well, very simple thing is potential energy depends of the position, not on speed. Whatever the speed, velocity of our particle is, it has nothing to do with this potential energy. So potential energy is independent of velocity and obviously its components, which means that du by dx prime equals to du by dy prime, which is du of dz prime, which is 0, independent of velocities. U depends only on potential energy, depends only on position. Great. Therefore, if instead of t we will put t minus u, nothing would change. But t minus u is Lagrangian. So we can safely put here Lagrangian. Now, why am I doing this? For a very simple reason. The definition of momentum, which I was talking before, x, y, and z, is basically applicable to three-dimensional world with Cartesian coordinates x, y, and z. That's why I have this formula, etc. Lagrangian, as you know, is basically applicable to any system of coordinates, Cartesian or non-Cartesian, generalized. So we can use Lagrangian with Cartesian coordinates. So, if these are Cartesian coordinates, then look at this equation. What I can do is, it's reasonable to assume that momentum, generalized momentum, it has k's coordinates, and it can be defined, that's a definition, as partial derivative by k's component of generalized velocity. This is a definition because it completely corresponds to Cartesian system. And that's it. Now let's talk about Noether's theorem. Noether's theorem is about symmetry of something causing conservation of something else. Like in the previous lecture, symmetry of time in a sense that Lagrangian is not changing if time is advanced by certain usually infinitesimal value. So if t is increasing by epsilon and Lagrangian is not changed, well, Lagrangian usually is not changed with the time if it doesn't depend on time. So if kinetic and potential energies formulas, which do depend on time, but internally, because it depends on position and velocities, and they depend on time, but there is no explicit dependency of Lagrangian by time. Then the partial derivative by time is equal to 0, and from this we derived in the previous lecture the energy conservation. Today, we will talk about different things. What if some coordinate is changed and it does not change Lagrangian? What happens in this case? Again, if time is changing, we have an energy conservation. If this coordinate, this particular coordinate is changed, which does not really affect Lagrangian, what happens in this case? Something else should be conserved, right? So let's talk about what exactly will be conserved. Now, if we change argument, the function is changed as well, right? Now, Lagrangian is the function of all coordinates and all time derivatives, and optionally on time. So in the previous lecture we decided that it's not dependent on time and came up with the law of energy conservation. Now in this case, let's find out what happens if one particular coordinate is changing, but it doesn't change the Lagrangian. So what happens? So somewhere here there is one particular thing which is qk, right, from 1 to n. So if I will have q plus epsilon here and subtract of q1, etc., qk, etc., qn, q1 strich, qn strich 10, what happens? Well, this is something which can be called an increment of Lagrangian. Well, Lagrangian is a function of many arguments. One particular argument is incremented by, let's say, infinitesimal, but well, whatever epsilon is, a small one. Now this is the previous value, qk, and this is qk plus epsilon. So the difference is we change the argument, incremented argument, it causes increment of the function. Now, what happens then? Well, let's talk about dl by dqk. What is this? Well, this is the limit of increment of Lagrangian of the function divided by increment of the argument, which is epsilon, but epsilon goes to 0. But we have assumed that if this happens, Lagrangian doesn't change, which means this is equal to 0. Which means this is equal to 0, which means this is equal to 0. So we have a partial derivative by qk equals to 0. And what happens now from here? If this is equal to 0, this is equal to 0. Now, what is this? By definition, it's a momentum. So what we have right now is a very simple equation d by dt of pk is equal to 0, which means pk is equal to constant. And that's exactly what's necessary to prove. We just came to this. This is the law of conservation of momentum. In this particular case, we are talking about one particular component. So if we increment this particular component and it does not change Lagrangian, if Lagrangian is invariant to translation, it's called translation. Pk goes to pk plus epsilon. It's a translation, it's a transformation by adding a constant. So if translation of one particular argument, well, I'm sorry, I should put q here. If one particular generalized coordinate component is changed, then the corresponding component of the momentum is not changed as well. So, and that's what it is, a symmetry of Lagrangian towards translation of generalized coordinate. Now, if it happens that many, several, more than one generalized coordinate is changed, and it does not really change Lagrangian, if Lagrangian is invariant to translation of several coordinates, so it will be several corresponding coordinates of the momentum conserved. If all of them, well, if all coordinates can be changed by something and it does not change Lagrangian, obviously that would be total momentum would be conserved. So basically that's it. I mean, the proof is just absolutely elementary of this thing. The key is obviously the Euler-Lagrange equation, and I would like to emphasize that this Lagrangian mechanics allows to approach our laws of conservation completely differently. So Noether's theorem applied to this particular case gives you the law of conservation of momentum basically instantly. All I did, I just used the definition of partial derivative, and considering the increment of the function is 0, it gives me partial derivative equals to 0, and partial derivative is actually a partial derivative by generalized coordinate. It's really the full time derivative of momentum, which gives you momentum conservation. Very simple. That's the power of Lagrangian and Noether's theorem. Okay. I don't know how difficult it was for Noether to come up with this type of logic. She was actually approaching everything mathematically. It's not like Lagrangian is, some physical things and etc. No, she was doing purely mathematical work, but it's 100% applicable to theoretical physics, and that's why it came up as such a, well, I would say, very unusual idea that something like preservation of invariance of Lagrangian of time gives you the law of energy conservation, or invariance of generalized coordinate translation gives you momentum. It was really kind of difficult even to imagine that there is such a connection. I mean, I was surprised when I learned about this, quite frankly. And I'm sure physicists like Einstein and others were surprised as well. They did not even think about what is the foundational matter. Basically, one particular equation, Lagrangian and Euler-Lagrange equation, these represent the laws of physics. So basically the whole thing means that the laws of physics, if Lagrangian is invariant, it means laws of physics, mechanics at least. But yes, it was actually much more than just mechanics. It goes to quantum physics as well. So this represents the laws of physics. So the whole thing philosophically means that the laws of physics are very much dependent on symmetries of time and space. So space is represented by generalized coordinates. So if they are in this way symmetrical, relative to, if laws of physics are symmetrical relative to translation of particular coordinate, then it represents something more fundamental than just empirical accepting these laws of physics. Like second law of Newton, we just accepted as an axiom when we started the Newtonian mechanics, right? And from this follow certain laws, etc. But if we accept as an axiom that the time is uniform or space is uniform, which means that change, if you will take this experiment and move it by time, let's say do it tomorrow, or move it by space, do it not in this but in this space, results are supposed to be the same if our time and space are basically uniformed everywhere, if there is no difference between here and there, or now and in the future, in this particular way. The laws of physics are the same. And that's what basically the fundamental properties of fundamental maybe results of Noether's theorem. So if the time and space are uniform, then the laws of physics are supposed to be such that conservation laws will be in place. Now let me give you a very, very small and simple example of what happens, basically an application of this particular law. What happens in this case? Well, let's consider you're on the surface of the Earth, so you're standing here and you're throwing a stone horizontally. Now, horizontally means that, well, let's say this is an x-axis, so x of t would be equal to some kind of a speed times time. Y would be the same, let's say 0, and what will be with the z coordinate, the vertical? Well, the z coordinate will be initial height minus 1/2 gt squared, if I'm not mistaken, right? So these are the laws of movement. Okay, fine. So what are the kinetic energy? Well, kinetic energy is, as we were saying, 1/2 mass times x prime square plus y prime square plus z times square. And derivative, now u is basically z times m times z, mass times height above the okay. Now, what is Lagrangian is the difference between them, right? So the Lagrangian by x prime, by x, sorry, let's talk by x, well, is equal to 0. Lagrangian by y is equal to 0. And Lagrangian by z is not 0, it's m. So we can expect that px would be equal to constant. Now, if speed is v along the x-axis, then px is mv, which is constant. Now, same thing here, py would be equal to constant, because it's m times py is m times speed, which is 0, it's constant. But pz will not be equal to constant. And we do see this exactly because the speed, the vz, would be increasing all the time, right? It's minus zt minus z prime, which is minus gt. That's the time derivative of z. So this is not constant, it's time dependent, and that's why this is not a constant. So basically that gives you exactly the same as we expected, whenever we are throwing horizontally a stone, since its horizontal speed is the same, its momentums projected to the x-axis would be the same. And this is this one. And y would be the same, because the speed, horizontal speed, would be the same. But vertical speed is increasing all the time, so momentum related to z coordinate would be increasing all the time. And that's what we have from here, obviously. There is no conservation of momentum along the z-axis. And obviously the total momentum vector is not equal to 0 because its z component is not equal to 0. Well, that's it. And so what I suggest you to do is, if you did not really do that before this lecture, do it now. Do it after the lecture. Read the notes. The same page in Unizor.com, go to Physics Plus, go to Lagrangian, and go to Noether's theorem about momentum conservation. Momentum conservation is basically mass. Momentum is mass times velocity, right? It's a vector. So you will see one of the lectures in the Lagrangian chapter would be called this way. Basically, that's it. Thank you very much, and good luck.